Hello everyone. In this video, we're going to be solving a really basic partial differential equation. I actually made a video on June 1st, 2025, a while ago, right? More than a year ago. I made the same problem. But at that time, we actually solved it using a different method called separation of variables. In this video, we're going to be using the method of characteristics, which is actually a really cool method for first order differential equations, and in some cases you can also solve higher order differential equations. So let's briefly talk about PDEs, partial differential equations, and then we're going to get into the solution. And my plan is to give you maybe once a week on this topic. Let me know what you think so that I can continue to do more problems on this one. So we have partial u over partial x equals partial u over partial. What is that supposed to mean? It kind of looks like a du over dx, but notice that u is a function of two variables in this case. So when we take the derivative, we first take the derivative with respect to x, meaning that we treat the y as a constant and vice versa. So there's definitely some shortcuts, but think about it this way. Let's look at some simple cases. For example, partial u over partial x, you can also say du, I guess, in this context because we know they're partial derivatives. Du over dx, let's say, is equal to x. How would you solve a differential equation like this? This is super duper basic, right? So you would probably integrate both sides, right? And your goal is to find u. So u is kind of like found by, since it's the derivative with respect to x, there's no y in it. You can directly integrate this, right? And if you integrate x with respect to x, you would get x squared divided by 2. And then, of course, you would add a constant, right? Yes and no. The constant doesn't have to be like a constant, but you can also add something, a function of y. And you're like, why? Because when you differentiate this with respect to x, f of y only contains y, which means there is no x in it. Its derivative will be 0. Does that make sense? That's why with partial differential equations, we use functions as constants most of the time, okay? So, of course, with the method of characteristics, constants are also going to come up, but in a different context. So let's go ahead and see how we can solve it. And in general, I can kind of give you a general idea. If you have a differential equation like something, let's just say a times ux. Oh, by the way, let me explain what u sub x means. So instead of writing this every time, the partial derivative of u with respect to x, we just write u sub x. That's what it means. And the other one we're going to denote by u sub y. And if it's successive derivatives, then we can do u xy, u yx. By the way, those two are the same if you have a really smooth, good function. Now, let's go ahead and write this with the ux format. So it's going to be like ux equals uy, right? So that's our goal. Whenever you have an equation like this, let's just say a times ux plus b times uy, and that is equal to some function, another function. Let's just call that u prime for now, because I'm going to define a parameter here, which I'm going to call s, okay? And then we're going to use that parameter to turn the PDE into an ODE, okay? And we're going to be using what's called characteristic curves, because along those curves, basically, our expression gives us a ODE instead of a PDE, okay? Now, if you try to put that into this format, then you're going to have something like 1 times ux minus 1 times uy equals 0. So in this case, the derivative of u happens to be 0, but derivative of u with respect to what, right? That's where we define our parameter. So we're going to replace a as a function of x and y, by the way. They're not constants necessarily. But we're going to replace it like this. We're going to call a dx over ds. These are ordinary derivatives, right? Not partial. Times ux plus dy over ds multiplied by uy. And guess what that's going to give us? From chain rule, this is going to give us du over ds. Of course, you can write it in a different form like dx over ds, and then this is going to be du over dx with the partials, and then dy over ds times the partials, right? And of course, you can see better why this is going to turn from into du over ds by using the chain rule, okay? So the x's kind of cancel out, but you kind of get a sum as well. So because there are two variables. Anyways, so here's what we're going to do. We're going to be looking at these numbers. That's what we're interested in. So what is dx over ds? What is dy over ds? Those are going to give us our characteristic curves. In this case, dx over ds happens to be 1. Okay, let me write that down. And dy over ds happens to be -1 because we subtracted uy from both sides. That's why it has a coefficient of 0. And du over ds, which is also very important in this case, happens to be 0. Why? Because there is nothing on the right-hand side. In other words, this is a homogeneous first-order partial differential equation with constant coefficients. Right? It cannot get any better, can it? Now, we're going to go ahead and solve each of these ODEs because they're very easy to solve. Obviously, from here, you immediately get dy is negative dx, right? If you compare them. And then from here, you can write this as y equals, if you integrate both sides, y equals negative x plus a constant. Now, this is the important part. We're not really interested in y in terms of x because our goal is to solve for u in terms of x and y, right? Because it's a function of x and y. So here's what we're going to do. We're going to isolate the constant. So we're going to add x to both sides. Now, this constant, of course, gives us a characteristic curve. Of course, constant is not like a constant because for every c, you do get a different curve. And we do need the c because we're basically describing different curves in the plane. Now, what happens with the u? Let's go ahead and save this, and then we'll come back to it. So we just said that du over ds is equal to 0. But s is the parameter, right, which gives us the characteristic curves. So from here, can't you say that u is constant? Yes, absolutely. From here, u is definitely a constant, and we can go ahead and call that c sub 1. Not the same c, but a c sub 1. Well, wait a minute. What is that supposed to mean? U is not everywhere constant. It's only constant along those characteristic curves. In this case, it's not like curvy curve, but it's those lines along which u is a constant. And here's what we're going to do. To associate the u constant with the characteristic constant, or the invariant, in other words, we're going to go ahead and do the following. The constant that comes from u, we're going to set it as a function of the constant that comes from the characteristic curve. That way, you can kind of associate for every characteristic curve, we do get the u value. Does that make sense? So basically, the constant depends on the characteristics. The x and y equations, which is dx over ds and dy over ds, those describe the path. And the u equation, in this case, it happens to be constant. It just describes the value along those paths. Okay? Now, we get the following. We said that c sub 1 is going to be a function of the c, but c is expressed as y plus x. Therefore, our solution is actually going to be f of y plus x because u is equal to that. So as a result, what's the solution to this PDE? F of y plus x, you can also write it as x plus y if you want, if you're obsessed about alphabetical order. So u is any function of x plus y. What is that supposed to mean? Let's go ahead and briefly talk about it. And in the next video, we're going to talk about other types. And I kind of try to make a sequence starting with the very basic ones. And we're going to go to the much, much harder ones. And trust me, there is hundreds of PDEs that we can do. If we do once a week, that's going to take us a couple of years to get through that. But anyways, let me know if you like these videos. So what does this mean? This means that any function of x plus y, right? For example, can f of x plus y be x plus y? Yes, if f of x is equal to x, then it's just the identity function. Can x plus y be a solution? Let's check it out. Differentiate this with respect to x. You're going to get 1 because the derivative of y is 0. Differentiate this with respect to y. The derivative of y is 1. The x is constant. So, as you can see, u of x is equal to uy. Now, what happens if you pick something more complicated, like, let's say, hey, I want to use u equals tangent x plus y, or e to the power x plus y. Guess what? You're always going to get the same relationship, ux equals uy. So as you can see, you can pretty much try any function of x plus y, and it is going to satisfy this equation. And also make sure to check out the other video, which I used a different method, and go ahead and compare these two methods. I'll share the link down below, and you can also check that video right here. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.